Hi everyone. So this is going to be part one of the lecture on the history of evolutionary thought. So make sure that you also are keeping an eye out to watch the second part, which I will upload at the same time. Okay, so the purpose of this section is to give you an idea of the background for how we came to understand evolutionary theory as we do today. So this is by no means exhaustive. This is very brief in comparison to some of the more in-depth looks we could take, but I do want everyone to have an idea of where we're coming from in terms of what we know of evolutionary theory. Okay, so if we go back in time, we can start with Aristotle and the Great Chain of Being. So people are probably familiar with the Great Chain of Being, the idea of it. I remember discussing it in junior high history class, if I'm remembering correctly. But basically, what I wanted to talk about a little bit was the starting point for modern evolutionary thought. Now, Aristotle, of course, was a 4th century BC Greek scholar. He believed that the form of everything was fixed. So the concept during Greek times was basically that everything was created exactly as it is today by the gods, and nothing has ever changed and nothing will ever change. So that's what we say when we say everything is fixed. So it can't be altered, everything exists as it always has. Now, beyond that, Aristotle also speculated that things could be arranged into a hierarchy of sorts. Now, this idea carried on until the Middle Ages, really. And you can see on the right-hand side of your screen an old artist's rendition of what the Great Chain of Being is represented as. Basically, the Great Chain of Being is an extension of Aristotle's original idea. So the concept of the Great Chain of Being, which was very prevalent, and it was really the only thing that was believed in the Middle Ages, is that every living thing has a fixed form and a fixed rank, and that everything has always been the same and always will be the same. So we're starting with a concept of fixity or immutability. So everything kind of stays the same in terms of thoughts of where life on Earth came from for a long, long time. And it isn't until the Renaissance, the 14th to the 16th centuries, where thinkers really started to speculate that things could possibly change over time. So Aristotle is important, even though he didn't have any concept of evolutionary change. He's still important because he was one of the first philosophers to try to apply human reason to understanding human nature, and nature in general. Okay, so this idea of the Great Chain of Being and the fixity of species, the fixity of life on Earth, really persists until the Middle Ages, as I said. So with the rise of Christianity, this idea kind of morphs a little bit. We have the introduction and the kind of widespread idea that the biblical Genesis account is a literal interpretation. That concept is a little bit similar. It just changes to the extent that the creation event took 7 24-hour days. But this idea of the fixity of species remains the same. Okay, so we're going to be going through several different thinkers, historical thinkers, and what they did or did not kind of contribute to our current understanding of evolutionary change. So that's kind of what we're going to be doing here. Now, we'll start with Archbishop James Ussher. He was an archbishop in the Church of Ireland. You can see the dates that he lived there. So Archbishop James Ussher was not a scientist. He was not a naturalist. He didn't have any kind of thoughts of exploring ideas of evolutionary change, anything like that. This time period is really too early for that. We don't see a widespread questioning of the fixity of species for quite some time. But Archbishop James Ussher is worth mentioning because some of his ideas have persisted in certain circles today. So Ussher wanted to determine the age of the Earth. So he obviously subscribed to a very strict interpretation of the biblical Genesis account of creation, and he wanted to try to figure out how old the Earth was. So he used the only information available to him at the time. Now, back in the 16th and 17th century, there was no knowledge of geology or anything like that. So basically what he used was information that was contained in the Bible. So he devised a method of determining the date of the creation event by counting the number of generations listed in the Old Testament. So there are sections in the Old Testament, as some of you may know, where it's just long lists of genealogical information. So he counted backwards using the ages of known major biblical figures, and he arrived at a date of the creation of the earth based on that information. Now, he estimated the date of the creation of the earth to be Saturday, October 22nd in the year 4004 BC. So this is an idea, again, like James Ussher didn't have, science as we know it today didn't exist during this time. And he was using the information that he had at hand to come up with what at the time was a reasonable answer to the question. Now, this date is still used by a certain segment of more conservative Christian groups. The young earth creationist movement still believes that this is the correct age of the earth. So if you've ever heard of young earth creationists, if you've ever heard that the earth was created 6,000 years ago, this is where the idea comes from. It was originally proposed by James Ussher. He also used other information in the Bible to kind of calculate significant dates of other things like Noah's flood and the Exodus. Okay, so up to this point, we still don't have any kind of firm scientific research or anything like that. So that brings us into the 18th century. A gentleman named Carl Linnaeus is who we're going to talk about next. Carl Linnaeus was a naturalist. The term naturalist basically means that he was kind of an amateur scientist. The term biology didn't exist at the time, but the kind of in the early origins of biology as a scientific field, these men referred to themselves as naturalists. So we're entering into the scientific revolution during the 18th century. Europeans during this time had begun circumnavigating the globe, so they were sailing around the world. They were coming into contact with new climates, new plants and animals, and all of this led to a lot of speculation about the diversity of life on Earth. So a lot of these thinkers at the time, these naturalists, were writing these long tracts talking about diversity of life on Earth, and Carl Linnaeus was one of the leading figures during this time. So he was part of this general trend of increasing interest in classifying organisms. So when we say classifying organisms, we mean naming them. We mean figuring out which organisms are closely related to other organisms. So basically looking at how living things relate to each other. Now, Linnaeus was a Swedish botanist. He developed the classification system, the naming system that we actually still use today in biology. So Linnaeus lived long before Darwin came around. Darwin was one of the earliest, he wasn't the first naturalist to argue for evolutionary change, but he was one of the first to propose a mechanism for it. So we'll get to that in a little bit. But just bearing in mind, during this time, there really weren't any well understood ideas of evolutionary change. So this was before any type of coherent narrative on how evolution could work. But he was still interested in this practice of taxonomy, of naming things and of figuring out how living things relate to each other. So he wrote a book, the name of which is on the slide here, called Systema Naturae, which means systems of nature. It was really his seminal work. It was a comprehensive classification of all life as he knew it on Earth. He was a botanist, so a lot of his work concerned plants, but he also wrote classifications for animals. Now, during Linnaeus's time, obviously nothing about genetics was known or anything like that. So he built his classification systems on physical attributes of plants and animals. So he looked at basically their physical appearance and he grouped them together based on that. So what he came up with is a naming system that is arranged into a hierarchy. So this system that he came up with back in the 18th century is referred to as Linnaean taxonomy. Now, as I said, today's system is rooted in Linnaeus's original work. You might remember this image here, something like it on the right. Back in high school biology class, you probably were exposed to it. This is Linnaeus's biological classification system. So when we say that it's rank-based, what we mean is that we start with this rank up top of life. So this rank at the top, meaning life, encompasses all life on Earth. So obviously that is a very wide category, a very broad category. The way that this biological classification system works is that as we go down this ladder, these categories become more and more narrow, more and more specific. So we have at the top here, we have life. Obviously, so all life on Earth, that's the broadest category you can possibly have. If we go down to this next category of domain, all animals have a domain that they belong to. We as humans belong in the eukarya domain, as opposed to prokaryotes. One step down to kingdom, we belong to the kingdom Animalia. So that includes all animals on Earth, but it excludes plants. So we started out with life, we narrowed it to domain, we've narrowed the categories even further to kingdom. If we go down one category to phylum, we come to phylum Chordata. This here that I have listed on the slide is the classification of humans, so we're using it as an example. This category of phylum, this taxonomic level of phylum for humans, we are included in the phylum Chordata. What that means is that we have spinal cords. So all animals on Earth that have spinal cords are included in the phylum Chordata. All invertebrates are included in other phyla. Stepping down another level here to the class Mammalia, we are mammals. We as human are mammals. We have mammary glands that females use to feed offspring. We produce milk, etc., etc. So class Mammalia, humans belong to class Mammalia, along with every other animal on the planet that has the ability to lactate. Now, if we step down again, we come to order Primates. This includes all animals that kind of vaguely look like us physically and behave like us. So humans, apes, monkeys, lemurs, lorises, tarsiers, all of those. So again, as you can see, we're starting wide and we're narrowing things down as we go further and further through this classification. If we skip all the way down to genus here, you've probably heard our species name before, our scientific name, which is Homo sapiens. We are members of the genus Homo and species Sapiens. So within the genus Homo, during modern times, we're the only members left of the genus Homo. But during previous periods in human evolution, there were other members of the genus that we shared the planet with, which we'll get into a lot later. So again, the thing to remember about the Linnaean taxonomy is that it's rank-based and that we still more or less use the same system that Linnaeus came up with. Now, the other thing that Linnaeus contributed to modern biology is something called the binomial nomenclature. So nomenclature just means naming system. Binomial means two-part. So binomial nomenclature means that when we refer to a scientific name of an organism, we always use this rank-based two-name system. So for humans, our scientific name in the binomial nomenclature is Homo sapiens. So it's these bottom two categories here, genus Homo, species Sapiens. Okay, so next up, we have Georges Louis Leclerc, the Comte de Buffon. We are still in the 18th century, still in a time period when we don't have a whole lot of coherent thought processes revolving around evolution, but we're kind of beginning to see the stirrings of thoughts about evolutionary change. So Leclerc was a French naturalist and mathematician. He believed, along with some of his compatriots, that evolutionary change could happen. So he was one of the early thinkers who were rejecting this idea of the fixity of species. He was beginning to speculate that organisms could change over time, that species could change over time. So this is kind of different from Linnaeus. If I didn't mention it before, Linnaeus didn't really believe in evolutionary change. He was a little too early for that. His goal, Linnaeus's goal in all of the work that he was doing was just to name God's creation. So Leclerc is a little bit different. He, again, is starting to speculate that biological change can occur, but he didn't understand the mechanisms. So one of his primary things that he's remembered for is something called Buffon's Law. Buffon's Law is stated there on the slide. Despite similar environments, different regions have unique plants and animals. This is really an important concept in the field of biogeography today. So biogeography is looking at what plants and animals live in what parts of the world and in what kind of climates. So he was just essentially observing that if you travel around the world to see different environments, whether they're cold, hot, wet, or dry, you're going to see different plants and animals living in different parts of the world. So he didn't really understand mechanisms of evolutionary change, but he definitely believed that evolutionary change could happen and probably explains why we see the diversity of life on Earth. He was declared a heretic by the Catholic Church, and he was excommunicated for these revolutionary ideas. Now, his work was really influential for later scholars. He was also one of the first to argue that the Earth was much likely a lot older than what Ussher had argued. So he was primarily kind of a voice of contention against Ussher's estimated age of the Earth, and that likely had a lot to do with why he was excommunicated. Okay, so that brings us to Jean-Baptiste Lamarck. We're moving forward in time as we go. We're getting into the early part of the 19th century. Lamarck was another French naturalist and also an early proponent of evolutionary change. So like Leclerc before him, he recognized the dynamic relationship between physical form and the environment. And he believed that you could use ideas of evolutionary change to explain why we see the diversity of life on Earth. He is primarily known for proposing something called the concept of the inheritance of acquired characteristics. Now, the inheritance of acquired characteristics is his mechanism, his proposed mechanism for evolutionary change. So Darwin proposed natural selection a little bit later in time, but Lamarck was really one of the first, if not the first scholars to put forth a coherent mechanism for how evolutionary change could happen. And I'll explain what his mechanism is in just a moment. So the picture that you see on the slide of this giraffe, this series of giraffes, is the classic diagram to explain Lamarck, what we could call Lamarckian evolution, his proposed mechanism. So Lamarck's giraffes, as you see here, are used to explain how physical form can change over the generations. So his explanation for how giraffes ended up with long necks, we can understand by looking at the slide. So what he proposes is that giraffes evolved or changed from an original short-necked ancestor. So that's what we see here on the left. Now that short-necked ancestor has really no problem reaching the leaves that it eats for food. Now, for whatever reason in this environment at some point during the past, the trees maybe were producing fewer leaves, whatever. The leaves became a little bit higher up off the ground. So the consequence is that this giraffe has to keep stretching its neck higher and higher and higher to reach the leaves that are high up on the tree. Now, this giraffe has a little bit longer of a neck than it did earlier in its life. Now, in this scheme of thinking, if this giraffe then has offspring, fathers or mothers a child, that offspring will also have a long neck. So it's passed its long neck off to its descendants. Now the process continues, the leaves get higher, these other generations of giraffes stretch their necks further and further. That characteristic is passed on from generation to generation, and eventually we end up with these modern giraffes that have very long necks. So when we say the inheritance of acquired characteristics, it means that characteristics that are acquired during an individual's life can be passed on to the offspring. Now, in order to understand this, we could maybe use an example for humans. If Lamarckian evolution was true, if you, let's say you're born a pretty skinny, kind of petite person, and you decide when you're in your 30s that you want to start weightlifting. Now, let's say you spend all of your time weightlifting every day for 5 years and you become really, really muscular. If Lamarckian evolution were true, if you then have offspring, either you father or mother a child, that child will be born more muscular, which we know, of course, doesn't happen. So we know that that's not the way genes work. Lamarck was not correct in his proposed mechanism for evolutionary change, but it's important because it was an important first step. As I said, really nobody had put together a coherent proposal for a mechanism for how evolution could work before Lamarck. So he did provide a service in that he was kind of stimulating thought in the scientific community about how evolutionary change could possibly happen. Okay, so moving on to George Cuvier. George Cuvier, again, we're moving further and further into the 19th century. Another Frenchman. During this time, ideas are starting to circulate in the scientific community in Western Europe about evolutionary change, but not everybody was on board. So the Catholic Church and religious communities were definitely a force against evolutionary thought, as they still are in some circles today. Basically, they held that ideas of evolutionary change were heretical and against the biblical account of creation. So during this time period, there was a lot of contention and a lot of debate about evolutionary change. A lot of scientists and naturalists during this time accepted evolutionary change, even if they didn't understand the exact mechanism, but plenty of them rejected the idea as well. Now, George Cuvier is one who definitely rejected ideas of evolutionary thought. He was not a religious person, though. His objections to evolutionary ideas were basically grounded in the fact that he didn't see any evidence of it in the natural world. So Cuvier was a paleontologist. As it says here, he's the father of modern paleontology. He was also a naturalist and an anatomist. One of his greatest contributions to science is that he introduced the idea of extinction, which of course has stood the test of time. He didn't support any modern ideas of evolutionary change, but because he was a paleontologist, he had access to all of the large fossil collections in Western Europe. So he could see that there were fossils of animals that existed in the past that no longer exist today. Now, one of the reasons why he didn't accept evolutionary change is because at the time, he simply did not see evidence of intermediate forms in the fossil record. So he believed that evolutionary change probably didn't happen because he would expect to see intermediate forms. Now, today, most fossil collections worldwide are a lot more extensive. A lot more species have been discovered since Cuvier's time, and the fossil record isn't as incomplete as it was during that time period. So now we have a better understanding of the paleontological record, and it's pretty much well accepted among scientists that we can see very clear progressions during the fossil record from one species to another. Okay, so the idea of catastrophism was his proposal for why we see extinction events happen, essentially. What he thought is that there were multiple creation events that were interspersed by great natural disasters. So in his mindset, the most recent natural disaster was the flood that is described in the Bible as Noah's flood. So he believed that there were these wide-scale extinction events due to catastrophic kind of natural disasters, but he did not accept that evolutionary change was possible. Now, one other thing that I'll say about Cuvier was that he wielded a lot of power in European circles in terms of scientists. So when he publicly made statements against evolution, it held a lot of weight. He was very influential and very powerful. And we'll come back to why that is important a little bit later. Okay, so we've got just one more person here before we get to Charles Darwin, and that is Charles Lyell. So Charles Lyell is considered to be the father of modern geology. He was a Scottish geologist who contributed a lot to the field of geology, and many of his contributions are still widely recognized to be true today. He was the first to find physical explanations for earthquakes and volcanoes. One of his biggest contributions is that he popularized the concept of uniformitarianism. So he had long been a proponent of the idea that the Earth is very old. So he, like some of the other people we've talked about, also rejected Ussher's 6,000-year estimation. So Lyell believed that the Earth was very old, and he used geological evidence to support that idea. So he was one of the, as I said, primary proponents of the concept of uniformitarianism. Uniformitarianism is the idea that the same gradual geological processes that we observe today were also operating in the past. So the example that I like to use, even though I don't think Charles Lyell ever went to the Grand Canyon, is the Grand Canyon. We know what caused the Grand Canyon. The physical process that caused the Grand Canyon can still be seen operating today. We have the Colorado River running down the center of the canyon. Basically, erosion over long periods of time is digging a hole digging this canyon into the surface of the earth, and it's getting deeper and deeper over time. So again, we know how this is working. We can see it happening in real time. We can see these erosion kind of processes happening as we watch. It just takes a long time for that amount of earth to be moved by erosion. So this is an example of uniformitarianism because if we use the Grand Canyon as an example, the Grand Canyon could not have been formed in 6,000 years. There's no way. There's no way that this geological process of the Colorado River cutting through and eroding these surfaces could have produced what we see in a mere 6,000 years. So he used physical, geological kind of phenomena like the Grand Canyon to push back against the idea that the Earth was very young. He didn't exactly know how old the Earth was, but he knew it had to be much, much older than 6,000 years. So that is the concept of uniformitarianism. Now, he's also important because he was a very close friend, really a lifelong friend of Charles Darwin. And Charles Darwin, who we will talk about next, was greatly influenced by Lyell's ideas. So we're going to get to Charles Darwin in just a moment. I just wanted to recap a little bit. So we've gone through time, starting with the Greeks and medieval Europe, with ideas of what's called the immutability of species, meaning the fixity, that things don't change. And we've gone a little bit through time discussing how certain members of the scientific community added to knowledge, kind of building over time to produce these evolutionary ideas that are starting to circle in the scientific community. So this really sets the stage for Charles Darwin and his theory of evolution by natural selection, which I will cover in the next slide set. So in part 2, I will cover that.